lines and planes. So a line can either be inside a plane, it can be parallel to the plane, or it can intersect the plane in only one position. By the way, if it is inside the plane, it's still technically parallel to the plane, but it also intercepts the plane. So it's parallel and it intercepts. And obviously if it intercepts in more than one point, then since it's a line, it has to be contained completely within the plane. Now when I say the line is inside the plane, I mean every single point on the line is also a point on the plane. Okay, so a line that is parallel to the plane, okay, to check whether a line is parallel to the plane, remember a line has a direction vector, so let's say B. So the equation of the line might look something like R is equal to A plus T times B, which is what we have here, and B determines the direction of the line. A is just an arbitrary vector to get us onto the line. Then the plane is going to have a normal vector, which we can calculate using the cross product. And this normal vector is orthogonal to every single vector that is contained within the plane. But if the line is parallel to the plane, it must also be orthogonal to the direction vector of the line. So therefore, we must have that b dot n is equal to 0. And that's the same for the case when the line is contained within the plane, obviously, because then the direction vector of the line is contained within the plane. And the definition of the normal vector is that it is orthogonal to every single vector contained in the plane, or parallel to the plane. Meanwhile, if we have a line that just intersects a plane in one position, then that means its direction vector is not orthogonal, let me use blue, not orthogonal to the normal vector. So this is the normal vector of the plane, and then we have our line, let's say it has this direction vector here, then in this situation we would have n dot b does not equal 0. And there's no other possibilities. So it's pretty easy stuff. You just take the direction vector of your line and the normal vector of the plane. You can take the dot product of them, and if you get something that's equal to 0, it means your line is either parallel to the plane or contained completely within the plane. To check which situation it is, you simply take any point on your line and see if it satisfies the equation of the plane as well. So let's now take a look at an example, exercise 6.8. The plane pi has the equation r dot 5 to negative 1 is equal to 28. So this is the normal vector, 5 to negative 1. And then it says for each line, determine whether it lies in the plane, is parallel to the plane, or intersects the plane. If the line intersects the plane, find the coordinates of intersection. Okay, so another way to write this is, of course, 5x plus 2y minus z is equal to 28. Don't need that right now, but can make use of it later perhaps. Okay, so for part A, we want to check if this line is inside this plane or if it's parallel to the plane or whatever. So first of all, let's check if it's parallel. And to do that, we can take the normal vector of the plane and dot product it with the direction vector of the line. So that will be negative 3, 1, 3, dotted with 5 to negative 1. That gives us negative 15 plus 2 minus 3, which does not equal 0. So we know immediately that this line just intercepts with the plane in one point. Like that. Otherwise, the dot product of the line, of the direction vector of the line and the normal vector would have to be 0. So since it's not 0, then we know that this angle here is not 90 degrees, and so therefore the line is not parallel to the plane. Alright, let's check out part B this time. So the direction vector of the line is -2, 9, 8. Let's check if it is orthogonal to the normal vector of the plane. So -2, 9, 8, dotted with the normal vector, which I believe is 5, 2, -1. What do we get this time? So we get -10 plus 18 minus 8. So absolutely this thing is equal to 0. So that means it is parallel to the plane, but it could be either inside the plane or it could just be parallel to the plane. So it could be, the line could be floating above with direction vector b equals, what was it, -2, 9, 8. Well, to check if it's actually inside the plane or not, so right now it could be either of these two situations. To check if it's inside, just take a point on the line. For example, when t equals 0, we have the point 4, 5, 2. Is 4, 5, 2 in the plane? Well, in order to check that, let's go ahead and look at the equation of pi, which is 5x plus 2y minus z equals 28. 5x plus 2y minus z equals 28. So we know we're in this situation if we have this point 4, 5, 2 that obeys this equation. And we have 5 times 4 is 20, plus 2 times 5 is 10, minus 2 gives us 28. So the answer is yes, 4, 5, 2 is in pi, so we have that our line is completely contained within the plane pi. And for part C, we have that the direction vector of our line is 3, -7, 1. And let's take the dot product of that with the normal vector of our line, which is 5, 2, -1. And we get 3 times 5 is 15, minus 14 minus 1 equals 0. So again, that places us in either one of these two situations. Either the line is contained completely within the plane, or it is parallel to the plane, since it is orthogonal to the normal vector of the plane. It has to be one of these two situations. Okay, well, in order to see which situation it is, we just have to check whether a point on this line is contained in the plane or not. So 619. So is 619 in the plane pi? So we just check using this equation. 5 times 6 is 30, plus 2 times 1 is 32, minus 9 does not equal 28. So no, it doesn't satisfy the equation 5x plus 2y minus z equals 28. So that means it must be parallel to the plane, but not inside the plane. Therefore, line is parallel to the plane pi, but not contained in